Hey there, Calc 3 folks, back here with another video in our study of vector calculus, where we are going to look at Green's theorem here. And in Green's theorem, what we're going to consider doing here is using the double integral calculation, right, to consider those, to use the double integral calculation to calculate what we call circulation and the cases for outward flux of some vector field over some curve C that exists in two-dimensional space, right? We had seen in previous videos calculating these values for the circulation and outward flux using what we call a linear integral. Well, that linear integral calculation can also be approached as a double integral calculation given by Green's theorem, right? Which is given as follows, right? Which we'll take note here is as follows, right? If we take a look at Green's theorem, and we'll get into it here, right? Green's theorem, we do assume that we have C as this simple closed curve in two-dimensional space that might be defined piecewise and orientated in some counterclockwise direction, right? That counterclockwise direction specific to this description of circulation, right? If C forms the boundary on a simple region we call R, simple region being just this closed region that doesn't necessarily overlap on itself, right? Or doesn't form with this intersection of itself, right? In two-dimensional space. If we have something like a disc shape or something like an oval shape or a portion within a triangle or a rectangle, right? These are simple closed regions in two-dimensional space, right? Then the circulation of F, the field, across that boundary given by C, right, is going to be given by, well, we understand this linear integral, which we saw for the circulation or the flow calculation back in the case for the linear integral of a vector field, right? Where we're going to calculate this linear integral of the vector field, giving us this circulation or flow calculation using this double integral calculation, where we can actually calculate the double integral over region R being the region bounded by our curve C, right? All with respect to the area of R, right? Integrate that double integral R with respect to the area of R, where our integrand is going to be the partial of G's description in our field with respect to X minus the partial of little f's description in our field with respect to Y. Where, if you take note, we are taking the double integral with respect to the area over this calculation, where this calculation here is actually the description of the curl seen on this vector field, right? We are, in a sense, integrating the curl across the field. And what we find is that if we integrate the curl value across this field, right, or I should say over the region of the field here defined by region R, if we integrate the curl across this region R, right, we do get an interpretation for what would be the circulation seen on the boundary of region R. All right, the circulation within a region determines the curl within a region determines the circulation on the boundary of that region, right, is what this theorem is telling us, right? And we do make formal note of that in our theorem here, right? We note in R2 that this quantity given by the integrand, the partial of G with respect to X minus the partial of F with respect to Y, is a description of the curl for this vector field at every single XY coordinate in that field, right? So what we are integrating when we perform this linear integral over this closed curve C that defines this simple region R, we are defining the curl, right? Or we are integrating the curl of that region R, right? At every single location in that field. We are, in a sense, adding up the curl at every single location in that region R And that is telling us the overall curl that we will see on the boundary, or the overall circulation that we will see on the boundary of R. All right. If we look at a specific example of this calculation, we might consider the circulation of the field -3y, 3x over the curve of C, right? The boundary on the triangular region in R2 with these vertices 0, 0, 1, 0, and 0, 2, right? That problem would be illustrated here as follows. Here we see our vector field, right? Vector field F, right? It is occurring both over this region of R that is bounded by this curve C. C being the simple closed curve defining this triangular region of space here in 2 dimensions, right? And as the field F occurs, right, over this region R, it is also occurring over this boundary of C, where we can talk about how is this field contributing to the flow of C, right? Contributing to the direction of change along this boundary of R that happens in this counterclockwise direction, right? How does the field contribute to that change in C, right, in the counterclockwise direction? And what we've been told with the theorem above, right, is that circulation measurement is really just a description of the curl at every single location in this field. If I want to describe here how we circulate around this boundary of R, right, I can consider what is the tendency of the field to want to rotate at every single point within R, right? The description of curl at every single point in R will give us an overall description of the circulation seen in the counterclockwise direction along the boundary of R here in 2-dimensional space, right? And we could calculate this linear integral calculation by breaking up our description of C into these 3 lines and performing that linear integral operation 3 times over each one of these lines and then adding it up. Or we can apply this double integral calculation seen for the curl over region R just once, where the boundary of region R can be set up as a double integral calculation. Well, in this case, if we consider that as our region of R, right, what we do note is this region R, not only is it defined by those 3 lines seen there in curve C, it is also the xy coordinates in space, where x happens between the values of 0 out to 1, and y happens between these boundaries starting at 0 and continuing up to this line, this diagonal line, this oblique line, given by 2 minus 2x. This becomes our boundary on region R, right? So for function, that field f of x comma y, right, given by -3y comma 3x, right, that linear integral over C can be approached as a double integral over R, right? We might say this. For this function here, this integrand's value, we might point out, is going to be equal to 3 minus -3, which equals 6 in value, right? And that double integral will produce this. Let's highlight this quantity in this calculation. Right? That, what we might call curl of our vector field, right, will be equal to 6, and our double integration will set itself up as this calculation seen here, right? Or our linear integration over that boundary of C, which corresponds to this double integration over region R, for what would be the curl with respect to the area of R, would set itself up in this manner. All right? It's just a double integral calculation defined by this description for region R in the rectangular space, where the inner integral happens across those functional bounds from 0 to 2 minus 2x with respect to y, and the outer integral happens across those constant bounds from 0 to 1 with respect to the variable of x. And this isn't a tricky integral calculation. This is a rather fundamental case, right? Where with my rewrite here, I can take out this step. Ooh, let's not take it all out. Let's see, can I get rid of that cleanly? There we go. All right. And this integral then, 6's integral with respect to y is just 6y, so pull the 6 out as a constant multiple and be left with y that has to be evaluated across these bounds from 0 to 2 minus 2x, which is just going to result in 2 minus 2x, which is now going to be integrated with respect to x. That's 2x minus x squared, and evaluated across the bounds from 0 to 1, which is really just 2 minus 1 in value, or 1. So it becomes 6 times 1, or the value of 6. All right? The curl at every single location in this region R is described by the value of 6. And if we integrate all of those curls at every single infinite point over R, it will tell us that the circulation on the boundary of this region R, defined by the curve C, is also the value of 6, right, in its measurement, in its description, right? This being produced by this field F seen here, where you would notice that it does appear that a positive curl measurement would be appropriate. If we look at how this field is behaving over this region R, or the curve C in the direction of the counterclockwise direction, first of all, within region R, what we would notice is if we had a bunch of paddle wheels at every single point in R, with the size of the vectors seen here in this field, right? That's almost too much. If we think about the size of the vectors seen here in this field, let's just leave it where it was. Too far in the delete. All right, the undo there. If we just look at the vectors in this field, there is going to be this propensity to want to rotate in the counterclockwise direction, right? If a paddle wheel was placed right here, the vectors pushing on the top of the paddle wheel as opposed to pushing on the bottom of the paddle wheel would be stronger, inevitably causing the paddle wheel to want to spin in the counterclockwise direction. Well, that is going to contribute to the circulation along the boundary of C. And if we think about how the field is behaving along this boundary, it does appear that along this edge of the field, or the curve C, right, the field is, and we think about moving in the counterclockwise direction, moving in this direction along C from the top to the, or from the bottom up here to the top corner, right, from the bottom right corner up here to the top of this triangle, right? A lot of the field is moving in the direction of that motion, right? Contributing to that motion in that direction. Whereas when you move down this vertical side of the triangle, you'll notice how that field is behaving across that boundary. Not much of it at all is moving either in the direction of the counterclockwise motion or opposed to it. It really is moving entirely, almost it appears orthogonal to that direction of motion. And we see a very similar behavior seen down here for the bottom of the triangle. It does appear most of the direction is moving orthogonal to this edge right, with that field behavior. So this would really produce a measurement of 0 for flow. This would be producing a measurement of 0 for flow, and this would be highlighting some positive measurement for flow. So 0 plus some positive measurement. That positive measurement must be what's equating to that flow of 6, right? Or that, what we might say is that curl of 6 at each of the locations here, or along this boundary, folks. All right. Again, the curl seen in the region R contributing to that outward, or that circulation around its outer edge. All right. Now that is Green's theorem used to calculate circulation, where we are looking at an integration over region R for the curl of the field, right? Where for outward flux, we do see a very similar setup, right? Where we are familiar with that as a linear integral calculation, as seen back in previous sections of material in our study of vector calculus, where we can now approach this linear integral calculation for the outward flux of this field across the curve C as really just a double integral calculation over the region of R defined by this curve C. Where you will notice that in this double integral over region R, your integrand is described by the partial of f with respect to x given by the field, added to the partial of g with respect to y, where little g is also given by the field. Where this sum of partials is the description for the divergence of the field. And what we're integrating over here as a double integral is over the total divergence across region R. Right? The total divergence across region R is going to describe the entire outward flux seen on the boundary of R, as we are setting up here in this form of Green's theorem for calculating outward flux. I do formally take note of that given down below here, right? We do note that the quantity given by this summation of partials does describe the divergence of the field, right? And what we are integrating in this linear integral calculation is a double integral calculation over the entire divergence of the field, well, over the divergence of the field over that entire region R, right? It is a calculation that sets itself up very similar, right, to that of the Green's theorem for circulation. In this case, we notice we do have this vector field f bar equal to x squared plus y squared comma 0, right? And it's happening over this curve C defined by the unit circle, right? The circle in the two-dimensional space centered at the origin with a radius of 1 unit, right? In this calculation, right, what we do notice is that C, right, can be defined by the parametric curve r of t equal to the cosine t sine of t for t in the interval from 0 to 2 pi. That if I was to approach this calculation in the context of the linear integral, I would be describing C as some circular curve described using this parametric description. Or it could be defined by the boundary on region R, where region R is defining this unit circle, whereas the values of x between -1 and 1, and the values of y between these two semicircles, the one below the x-axis with a radius of 1 and the one above the x-axis with the radius of 1. Where how we are going to consider approaching the calculation, right? Well, I will point out as if we consider approaching then this linear integral calculation seen here as this double integral for how we've defined region R, that calculation would set itself up as this statement here, which isn't necessarily terribly unbearable, but can also be approached, I will point out, because of our region R being described as some circular region, right, bounded by this the circle's description, right? We can say that that region R is also described in the polar context as just the values of R and theta, where theta happens between 0 and 2 pi, and R is between the values of 0 and 1, where I can then take this rectangular interpretation of this double integral calculation over region R for the divergence of f bar and consider its calculation, right, in terms of the polar context. Now, one thing I didn't point out here is note the divergence of f bar is given by 2x. It's in this case, C can be defined as this, right? F bar equals this. So the outward, hold on, let me fix this real quick, just to make sure something is a little clearer to begin with. Okay, there, folks, I think I fixed it. I did want to point out specifically where the divergence is coming from in this calculation, right? So when we think about this linear integral operator for the outward flux in this case, which is going to be approached as this double integral calculation, right? Since our vector field is described by this, the divergence is really just going to be the partial of this first term with respect to x plus the partial of the second with respect to y. So this will be 2x plus 0, which is just 2x. Right? We might highlight that. That's equal to 2x plus 0 in value, which is just equal to 2x. And then that linear integral calculation for outward flux could be interpreted as this double integral calculation seen here, where because we are describing a region that is simply stated in the polar context as this region R, where theta is between 0 and 2 pi and R is between 0 and 1 in the polar context, we can now consider approaching this double integral calculation for this outward flux in the polar context as the calculation seen here, where we can consider integrating with respect to R and theta across the bounds as we've noted here in our description of R, theta from 0 to 2 pi, R from 0 to 1, where if we translate the divergence of f bar 2x to the polar context, keep in mind x is going to turn into the r cosine theta. And in this polar transformation of a double integral, we include that one scalar factor, right? That Jacobian multiplier given by the value of a little r. This is going to become 2r squared as an integrand, where we integrate first with respect to r, and that gives us the result 2/3 r cubed cosine theta. And we note that antiderivative is seen here. All right, this is going to turn into r squared, so that's going to bump up to a power of 3, divide by 3, and you're going to get 2/3 r cubed cosine theta. Evaluated across the bounds from 0 to 1 for r, that's just going to make 2/3 cosine theta. We'll factor the 2/3 out as a constant multiple. So we'll be integrating 0 to 2 pi, the argument of cosine theta, where this does happen in these integrals. All right, we get an antiderivative of sine theta for cosine theta, where when I consider evaluating that across the bounds from 0 to 2 pi, that calculation is nothing more than the value of 0. So it is 2/3 times 0, which is just 0 in value. All right, that is the double integral calculation that produces the outward flux for this consideration seen here. Now, to understand that 0 calculation, let's look at the illustration. I didn't want to give away the 0 calculation too soon. All right, but you might be able to see it here in this illustration of why this outward flux is being calculated as 0. And if we look at the illustration seen here, right, the value we're calculating is the field's tendency to want to move across this unit circle orthogonal to the unit circle. And if we think about the field's behavior moving across the unit circle here, it is moving from, in a sense, left to right in our illustration, right? It is starting in the negative direction of y and moving to the positive direction of x in this very symmetrical behavior with respect to x. As we move further from x, or really I should say as we move further from the origin, right, we have this rightward behavior, right, this push to the right that grows in magnitude, right, in both the positive and negative directions for x and y's change, right? Where if we notice on the boundary here, for the right half of this boundary C, it appears most of the field is moving outward, right? Or actually, the field is actually pushing in the outward direction. It is, in a sense, diverging away from this half of this circle, the unit circle. Whereas if you look at the other symmetrical half of that unit circle, the left half, the entire field appears to be moving or converging on that boundary, right? And the amount that we're converging on that boundary, along that boundary of C, appears to be balanced with the amount that's diverging away on the right half of this circle. In terms of the entire outward flux of that circle along the entire boundary of that circle, we do see there is no well, we might say here a net flux measurement that balances at the value of 0. The amount that's moving out on the right half of that boundary is equivalent to the amount that's moving in at the left half of that boundary. And all that is being also described in this case for Green's theorem by considering how are all the points diverging, right, in this region of R. And how all these points are diverging in this region of R, right? That's all described by 2 times x. That just depends upon the value of x, right? For values to the right of R here, it's going to be 2 times positive values of x. And to values to the left, it's going to be 2 times negative values of x. And there is just the same, there's the exact same amount of values to the left of the y-axis where you have negative x values, where the convergence on those points yielding negative values is equivalent to the divergence that we see at all these points on the right half of region R, right, where we're diverging away by a value of 2 times x for positive values of x, right? That balanced divergence across this region of R is what helps to describe, or is what we're using to describe, the outward flux on this circulation of C, and that it's that motion across the boundary orthogonal to that boundary of C. And the amount we have moving orthogonal to that boundary is balanced across this entire circular boundary. The amount moving across on the right-hand side is balanced, well, I should say moving out on the right-hand side is balanced by the amount that's moving in on the left. All right, so it does give us a outward flux calculation across that boundary of C being 0, where we calculated that using the divergence found within region of R, right, as a double integral calculation, right? Again, folks, that is using what we call Green's theorem. Green's theorem makes the connection of the linear integral operations of outward flux and circulation, right, to this double integration involving either the case of curl, right, for the case of circulation, and divergence for the case of outward flux, where we are double integrating over region R, though values for the entire divergence over that region or the entire curl over that region, right? And the double integral of the entire divergence over that region of R gives us the entire the measurement for outward flux across its bounds, and the curl, right, the double integral of the entire curl across region R gives us the measurement for the circulation along its bounds. All right? So folks, that is just a little further into the study of vector calculus, where we are staying on these topics of what we might call flux and flow, specific to the case of closed regions, right? Where flow turns into circulation and flux becomes this description of outward flux. And looking at here in Green's theorem, the ability that when we have these nice simple closed regions, being able to use the divergence and curl in the form of a double integral over that region to calculate these linear integrals that we discovered earlier as circulation and outward flux, right, along the boundary of that region, right? Now, what we are going to continue on to in the notes is we are going to continue with what are surface integrals, right? We're going to make an analogical connection to the case of linear integrals being an integration across a line to the idea of being an integration across a surface. And in fact, you might already start to note here that what we were calculating in Green's theorem, right? This calculation seen here, this calculation summarized as the curl over region R, is actually describing a surface integral. We are integrating at every single point in this surface. And what are we integrating at every single point in this surface is the measurement of curl, right? That surface being region R here in two-dimensional space. And we are calculating a surface integral down here in the case of outward flux, right? Where our surface is this region R given by the region bounded by the unit circle here in two-dimensional space, where we are integrating across that entire surface the value of the divergence seen by our field here. And that is giving us this outward flux measurement, right? So Green's theorem is already highlighting the cases for surface integrals, right? Anytime we have calculated a double integral in the past, we are, and now with Green's theorem, we are calculating a more generic understanding of integration, which is the case of surface integration, integration across a surface, where a single integration had a generic understanding of integration across a line. And there are going to be, as we've seen with linear integrations, moving outside of what is a description of one-dimensional space and the n-dimensional for lines. Here in the analogical case of surface integrals, moving outside of some surface description in 2 dimensions to what if we had some surface description in 3 dimensions? How would we integrate across a 2-dimensional surface that itself is curved in the 3rd dimension, right? That is going to require some transformation, right? That's analogous to the transformation that we saw when moving outside of the one-dimensional space where we described linear integration in our previous study to allowing that one-dimensional description of a line to be able to be warped in n-dimensional space. All right, so folks, that is where we're heading. I hope you're hanging in there. We're almost done. The last couple of videos here are really on some quick ideas and shouldn't take too long to put out. I have a lot of the notes written already, except for our last section. And much of it involves, outside of here, once we get into surface integrals, some really quick calculations, folks, and some really quick theorems. It's not going to be very heavy, I hope, in terms of the material. So hang in there. We're almost done. I'll see you in the next video.